And today, for our IQIM seminar, we have Ashley Milsted, who joined Caltech a bit less than a year ago. Is that correct, right?
Well, it's quite a bit less than a year, and then October, I guess, yeah.
And you were coming from Perimeter.
Yeah, that's right.
And today you're going to talk us about false vacuum bubbles.
I sure am.
So please.
All right, so yeah, so this is work with Junyu Liu, grad student here at Caltech, and John Preskill and Geoffrey Vidal, who's at the Alphabet subsidiary X, formerly known as Google X at the moment. And the work is about collapse of false vacuum bubbles in spin chain systems. So what do I mean by a false vacuum? Well, this is often thought of in quantum field theories. And in a quantum field theory, one can often write down an effective potential that tells you something about the vacua or the vacuum of the theory. And for example, in symmetry broken lambda phi 4 theory, one has an effective potential that has a double potential well. This is real scalar field theory. A double well, and so there are two equally good vacua or ground states of this potential. And this is a situation where there is spontaneous symmetry breaking. So, you would expect to be in one of these wells rather than the other. So two equally good true vacua. But if we explicitly break the symmetry here, this Z2 symmetry, by say applying a field, then one of these vacua now becomes a local minimum of the potential, and the global minimum is somewhere else. And it's possible that you can have a state which looks, for all practical purposes, much like a vacuum in one of the in this now local minimum, which, however, over long timescales is expected to decay to the true vacuum. So this is an explicitly broken symmetry. And the decay process could be thermal, but it could also be a quantum tunneling process that takes you to the true vacuum. And if you start in the false vacuum, then what you would expect is that maybe due to some local process, some local fluctuation, let's say, a bubble of the true vacuum starts to form in space, and then it will expand and expand because it's energetically favorable for it to do so until it takes up the entire universe. So that certainly sounds pretty catastrophic, and you might worry that this actually could happen to us because if you just take the standard model, apparently, and I don't know very much about the standard model, it's not my specialty, but apparently from looking at the mass of the top quark and the Higgs boson, you can estimate whether we're in a stable state, a stable vacuum, or whether we're in a metastable vacuum, a false vacuum. And apparently the data that we have suggests we may be in a metastable region, assuming that we just have the standard model. Of course, if you go beyond the standard model, there might be stabilizing mechanisms that change this picture. But still, that means you might be worried we might be living in a false vacuum, and someday a seed of true vacuum might appear and rush out to encompass the universe that we know and destroy everything in its path. So on that depressing note, let's look at a 1+1 dimensional version of this picture at late times. So at late times, the false vacuum has been collapsing, and now we're thinking about a situation where there are two regions of true vacuum rushing in to destroy the last remaining bubble of false vacuum in the middle of the system. So there are these walls, these bubble walls, the bubble being the bubble of false vacuum in the middle, that are rushing towards each other at the speed of light, say, and eventually they crash into each other and stuff happens. Presumably particles are created and fly off at high energies. Now particles that are living on the true vacuum sector. So the question we want to answer is, can we compute the dynamics of this process of false vacuum bubble collapse? So ideally, of course, we'd like to do this for say, the standard model and figure out what standard model particles are created when this happens. But of course, this is a very complicated interacting quantum field theory in 3+1 dimensions, and it's just way too hard. So we're not going to do that. One simplification might be to look at part of the standard model. So we have a real scalar field in the well, I don't know if it's real. We have a scalar field in the standard model. And a simple interacting scalar field theory is 5-4 theory. And we could make it even simpler. We could go to 1+1 dimensions. You can still set up this scenario there. Now this is now a simple, compared to the standard model, interacting quantum field theory. And you can do some perturbative calculations for this at weak coupling. But again, you can't access phenomena at strong coupling, which you'd like to do if the energy gets cranked up and you have these bubble walls colliding at the speed of light. So that we could try to figure out how to do strong coupling calculations. And one way to do that is to go to the lattice, discretize, regularize the system. And when you discretize 5-4 theory, you end up with a chain of bosonic particles. And that's great because you can now do tensor network calculations. You can simulate real-time dynamics using, say, matrix product states. But there's a problem that complicates matters, which is that now you have bosonic particles on each lattice site, and a bosonic particle has still an infinitely large Hilbert space, and you have to truncate that somehow to do an actual concrete calculation. So we are going to go to the even simpler setting of spin chains, where we have a finite Hilbert space dimension for each lattice site, and we no longer need to do truncation. I see that there's a question in the Q&A. I'm going to stop for that in a second. But before I do that, I want to say, so of course, each step of the way here, we're losing some physics, losing some physical phenomena, and we're getting further from the standard model. But we can still hope to find at least some minimal shared phenomena in the spin chain setting that helps us to understand the physics of the more complicated scenario. So we're going to focus on spin chains. Now, this is a pretty good place. Well, I'll just show you this slide to illustrate what I mean by focusing on spin chains first. So a spin chain now being a chain of these discrete particles, say qubits that can be either in the up or down state. And now the false vacuum bubble looks like this. There's some domain wall-like structure, and the domain walls are rushing toward each other to eat up this bubble of false vacuum. Okay, I'm going to look at the question now. Why can't areas in the center of the bubble convert to the true vacuum? Does the conversion need to occur at the boundary of false and true vacuum? From Nate. Answer live. Yeah, I'm answering this question live. I haven't done this before. Okay. Yeah, the answer to that question is yes. If there is a process that can spontaneously form a true vacuum bubble in the first place, then there must be processes that can turn the false vacuum in the middle of the picture, say in this picture here. There ought to be processes that can turn that into true vacuum as well. But we will be studying cases where this process is extremely unlikely. So we will artificially create a bubble of false vacuum, assume that this unlikely event has happened at least once. But the chances of it happening during our simulation in the middle of this false vacuum bubble are minuscule. I hope that answers the question. Okay. If there are any more questions right now, feel free to pipe up.
There is another question.
Okay, yeah, you could use fermions for 5-4 theory, so no need to do truncation. It is possible. Well, could you use fermions? So you can use fermions for scalar field theory in the symmetry broken phase. Well, oh, I got another question as well. But I guess I don't know then how the lattice discretization would look. It would presumably be a chain of interacting fermions. If the interactions are local, that's potentially doable, but it's hard to do. You know, the easiest way typically of simulating a chain of interacting fermions is to actually do a Jordan-Wigner transformation and turn it into a chain of interacting spins. So I think probably, I don't think there's something to be gained from looking at the fermion picture, but it's not something I've thought about very much, so maybe there is. Another question, what are the processes that drive domain walls to move? Okay, great. So that's driven by the explicit symmetry breaking field that I mentioned that you need to split the effective potential and create a false vacuum out of one of the potential true vacua in the spontaneous symmetry broken case. So this is an external field that just favors the true vacuum over the false vacuum. So in the case of spins, it's a field that favors, say, spin up rather than spin down. And generically, that will introduce an accelerating force for a domain wall or a kink like this. I hope that answers that question. Okay. All right, I'll keep going then. So the project that we took on is to figure out how to, in the spin chain scenario, construct bubbles of false vacuum. So construct an initial state for a bubble of the false vacuum, and then simulate the collapse of this bubble in real time. And to do this, we're using infinite matrix product states to avoid boundary effects complicating things. We want to then, of course, be able to characterize the physics. So we want to figure out, say, what particles are being produced when the bubble collapses. And also, since we're in this spin chain scenario where, you know, we don't necessarily know what physics to expect, there is a whole menagerie of spin chains one could look at for this. There's the question of which spin chains are actually interesting for studying these phenomena. A boring spin chain, for example, might produce purely elastic scattering, in which a false vacuum bubble simply bounces and never generates any new particles. And finally, we want to understand in detail for this particular kind of problem the computational requirements. So simulating real-time evolution using tensor networks, in this case matrix product states, is generically a hard thing to do, in the sense that the computational cost scales exponentially in the amount of time that you want to simulate. That's the generic statement. Now, in particular cases, you will be able to get to shorter times or longer times, and we want to see how far we can go in this particular kind of physical scenario. There's a question? Oh, there are some more.
There is a follow-up to one of the previous questions. So
oh, sure. Yeah, okay.
You can answer that before you...
Yeah, I should do that before I move on. So it's a follow-up to the question of what process drives the domain walls to move. And the follow-up is, but why does that process just drive the wall to move instead of allowing the middle part to convert? Okay, good. Yes. So this is related to a previous question of why don't we spontaneously get true vacuum bubbles forming in the middle during the simulation? And the trick is to just turn this this field on with a very small coefficient. If the coefficient is sufficiently small, the larger it is, the more likely that this false vacuum will spontaneously decay to the true vacuum. And also the faster the accelerating force. But if you turn it on only a little bit, compared to the other terms in the Hamiltonian, then the process is very unlikely of spontaneous decay, and the accelerating force on the walls is still sufficient to get interesting things happening. So if this field is too strong, then you no longer really have the metastability of the false vacuum state, but we want to be in the regime where we have a metastable false vacuum state that lasts a long, long time. And there's another component to this. So it seems to me that those processes change the shape of the potentials. Well, so the field that breaks the symmetry explicitly indeed changes the shape of the potential. I mean, I guess I showed you a diagram illustrating that on one of the first slides, but I guess maybe that's not what you mean. Generically, it will, be a little bit more complicated than just shifting the minima away from each other. But for small values of this field, the effect should be approximately just that. Okay. All right, did I get everything? I think open, oh, these are, I need to say done. I'm going to say done to these so that they no longer show up. Okay, good. All right. So results of this project so far, we can indeed construct stable bubble wall states. So this involves creating wave packets for kink-like excitations in the model, and we can indeed construct stable wave packets such that the spread is very small as time evolves, and essentially you just see a kink moving rather than a kink dispersing throughout the system. We have found that in possibly the simplest spin chain setting for this, the transverse field Ising model, that you do essentially just see elastic collapse of false vacuum bubbles, which surprises us a little bit, because if you add the longitudinal field needed to break the Z2 symmetry of the Ising model, this is no longer an integrable system, so you would generically expect inelastic scattering, but we find that at least in the case of collapsing false vacuum bubbles, we only observe elastic scattering despite this. And we extended the model to explore one that did indeed involve inelastic scattering, and I'll show you results demonstrating that we have inelastic scattering later. Okay, so I'm going to tell you a little bit about the methods that we use for this. And as I mentioned, it's matrix product states, and we'll be constructing wave packets. So what states do we need for the simulation? Well, we need the true and the false vacua. So in the spin chain, this is something like the all spin up state for the true vacuum and the all spin down state for the false vacuum. But that's in the case where the interaction is turned off. Where the interaction is turned on, there will be dressed versions of these states where there are correlations spatially. And we'll need matrix product states to represent them accurately. And for the bubble walls, we'll have something like a domain wall, but again, it'll be dressed. So rather than just having a sharp change from spin up to spin down, there'll be some sort of a smooth dressed domain wall that we'll use to build our bubble wall states. There's another question here, so I'll quickly check what it is. Are the stable kinks at all related to the quasiparticle kinks appearing in the sine-Gordon model? I think the answer is yes. I'm not too familiar with the physics of the sine-Gordon model, except that I know it supports kink-like excitations. In the classical sine-Gordon model, there are exact kink solutions to the classical equations of motion, so solitons. But in the quantum case, and that's essentially true for the spin chain as well. If you turn the interaction off, there are exact eigenstates of the Hamiltonian that are kinks. But as soon as you turn the interaction on in the quantum case, then although you can have stable quasiparticles localized, there's still some slow spread of these things. They're not solitons in the sense that they do slowly spread out with time. But what I can say is that there are exact eigenstates of the Hamiltonian that are kinks, but these are not localized. These are momentum eigenstates. So I hope that goes some way to answering that question. Done. Okay. So how do we represent our quantum states? So I'm going to assume you don't know much about tensor networks or matrix product states, and briefly remind you or explain what those are. So here's a generic way of writing a state of 3 spins, these 3 balls here. We take some basis where we separate the spins spatially, I, J, and K, and then we write the wave function as coefficients for that basis, psi, I, J, K. Now we can rewrite that wave function as in pictorial form, in diagrammatic form, as a blob. And this blob is now a tensor network diagram. and this blob in particular is a tensor. And each of the legs on this blob represents one of the indices of this tensor. And a matrix product state is simply a way of decomposing this tensor, this single psi tensor, into multiple tensors. So now we have a single tensor for each site, each spin in the system, and we connect them so that there can be correlations between the different lattice sites. We connect them with new indices, which we call bonds, which we contract over in this sum here. And depending on the dimension of these bonds, we can represent different classes of states. And if you allow the bonds to have arbitrarily high dimension, you can represent any state in this format. So that's a matrix product state. Now, matrix product states, I mentioned that these guys are called bonds, and the dimension I'm going to denote with the letter chi. These physical legs, as a reminder, these legs going vertically are the physical indices of the system. They represent the spins, as a reminder. And it's worth pointing out that computations with matrix product states typically have a time cost of order chi cubed, because they mostly just involve chi by chi matrix multiplications. Now, interesting property of the matrix product state is that the dimension chi determines how much entanglement the state can support on bipartitions. So if you just make a cut in your matrix product state between the left and the right side, then the dimension of the bond that you cut determines the maximum von Neumann entropy in the following way. So S is less than or equal to log of chi. So that's important. It means that we can efficiently represent states with a moderate amount of entanglement, but if the entanglement grows too fast, then it becomes difficult. And hence, generically with real-time evolution, where entanglement generically grows linearly with time, you quickly get to the point where to represent the state accurately, your bond dimension has to grow too fast. It has to grow exponentially with time. And once it grows beyond a certain point, you can no longer fit the thing in your computer or do the calculations efficiently. Okay, so for the vacua, we're going to use infinite matrix product states. So we go from this all spin up state of the non-interacting spin chain to addressed state represented by a matrix product state. And the bonds here allow correlations between lattice sites, which are necessary to represent the ground state of the interacting chain. So we find these tensors that make up the matrix product state by energy minimization. It's a variational technique. And for the false vacuum, because we have this symmetry breaking potential, we simply first flip all the spins from the true vacuum. That's essentially a free operation on the matrix product state. And then we do a further energy minimization and cool the state down to a false vacuum approximate eigenstate. Now, this is related to what I said before. If the symmetry breaking field is sufficiently small, for all practical purposes, there is a false vacuum eigenstate that you can reach in this way. If the potential is too large, if the field is too strong, then you won't be able to find a metastable false vacuum state in this way. Okay. Now, so we've got the true and the false vacuum now, but we still need to represent these kinks. So how do we do that? Well, we take the tensors from the true vacuum matrix product state and from the false vacuum matrix product state. We join them together and we allow the tensor in the middle to vary to represent some dressed kink that is a dressed version of this simple domain wall. How do we find this tensor, this green tensor here? Well, we solve for the momentum eigenstates of the Hamiltonian in this topologically non-trivial sector. So we build momentum eigenstates by just summing up these localized contributions, and we solve the effective Hamiltonian. This is a technique that's been used for some time, and it can treat also topologically trivial excitations, I should point out. So what we have is a state that looks like this. Is just some momentum eigenstate formed from these position basis states, if you like. And if you solve the effective Hamiltonian, you find some dispersion relation for some excitations in your system. So this is energy, this is momentum. You can choose the momentum here. You solve the Hamiltonian in each momentum sector, and you find there's some, say, a branch of low energy kink-like excitations like this. And I will look at what the question is. Let's see. Does it matter that tensors live on sites whereas kinks live on bonds? Good question. So you could have, instead of having a green tensor in the middle here, you could have put a matrix, a tensor just on the bond without a physical site index. And then you would think about it as living on the bond. That would also be a valid way of proceeding and trying to approximate these kink-like excitations, but you'd have fewer parameters to work with. You have more parameters if you allow a full site tensor to vary. And in fact, you can generalize this further and say, well, I want a tensor which encompasses 2 sites or 3 sites and go further. And that increases the number of variational parameters and in principle, the accuracy of the state you find. So we could make them live on the bonds, but it's more accurate to, you get more accurate results if you allow them to live on a site or even a bunch of sites. Okay. So wave packets. So now that we have found these green tensors for these momentum eigenstates, we're going to use these position basis states with the optimal green tensor to build wave packets. So then we still sum up over these position basis states, but now we have some envelope function, some packet function f, which say is a Gaussian. And we could make it quite a localized Gaussian, localized in space, in which case it would have quite a broad support on this branch of low energy kinks. Or we could make it broader in space, in which case it has a narrower support on the momenta. And actually, we're going to want it to have a narrow range of momenta because that will make it a more stable wave packet. If you think about how group velocity works and how wave packet dynamics work, then you know, the more linear the dispersion relation is, where you have support on it, the better for the stability of your wave packet. Okay, so constructing wave packets like this from these excitations has been done recently in the literature, not for these kink-like states, but for topologically trivial excitations. And we're doing it for these kinks, and we're going to extend it a little further as well. Okay, so now we have true and false vacua, and we have the bubble wall kink-like states, both dressed appropriately for the interacting system. So how do we do our simulation? Well, we construct an initial state for this false vacuum bubble. It's going to consist of 2 kinks, 2 green tensors, with true vacuum on the outside and false vacuum on the inside. And we have some packet function for this 2 kink basis, which is just a product of 2 Gaussian packets, which are sufficiently far apart that we don't have to worry about interactions between the kinks. And then what we do is we just time evolve this state, this initial state. I should point out that the bond dimension of such a state is only twice the bond dimension of the vacuum state. So constructing these packets is not a costly thing to do. And so we can simulate the time evolution, at least for short times, reasonably easily. So we do that within a finite non-uniform window of the infinite spin chain in order not to have boundary effects from a finite chain. And once we have our simulation and we have states at later times, we want to analyze the particle content of those states. So we're going to actually reuse these position basis states, not only for kinks, but also for topologically trivial scalar particles, if you like. And we're going to just take overlaps with these states in order to diagnose the particle content. So I'm going to stop briefly in case there are any more questions on that section, which I suppose there aren't. Okay, so the model that we're looking at is a spin chain model And I'm going to skip the pure Ising case because, as I mentioned, that was boring and elastic. And we're going to go straight to a modified Ising chain, which has both Ising and tricritical Ising criticality. So the minimal criteria we might want from a spin chain model for this sort of phenomenon is, well, we at least need it to have a false vacuum. So it needs to have symmetry breaking, and we need to be able to split that to break that symmetry explicitly. We want it to have inelastic bubble collapse, so that interesting stuff happens rather than just bouncing. And we want the simulation to be reasonably efficient. So we don't, for example, want the number of states per site to be too high. So the concrete model is in fact the Ising spin chain plus an extra term. So these are just the Pauli matrices Z, X, Z. And the extra term, ZZX plus XZZ, controlled by this parameter lambda, serves to push you toward a tricritical Ising critical point. That is, if you stay on the line of self-duality of this model, for those who know what that means. So this Z field is the one that explicitly breaks the Z2 symmetry that would otherwise be present in this model. And we turn this H on only a little bit so that we have metastable false vacuum states. It has interesting dynamics, at least you would think it would, because it's certainly not an integrable spin chain, and it's not close to an integrable spin chain. And it's a qubit chain still, so we expect to be able to do this efficiently. So the phase diagram, for those who are interested, looks something like this. The critical Ising point is G equal to 1 and lambda equal to 0. And if you turn on lambda, then this Ising criticality extends into a line, and eventually you end on a tricritical Ising point. And I'm going to show you simulations from this green X here, which is sufficiently close to the tricritical Ising point to be influenced by its physics, which allows us to get away from the pure Ising case, which, as I mentioned, isn't particularly interesting. This point on the diagram, by the way, is indeed has spontaneous symmetry breaking in the absence of this Z field, and when we turn on the Z field, we explicitly break the Z2 symmetry. Oh, I should point out, this model was studied recently by O'Brien and Edward O'Brien and Paul Fendley in the context of interacting fermions and supersymmetry. Okay, so let's get on to some results. Hopefully everyone's still awake, because it's maybe going to get more interesting now. So let me show you that, let me try to convince you that we can indeed construct stable kink quasiparticle states. So this is just a plot of the spin expectation value as a function of position, showing some kink-like excitation. So this is a kink wave packet built from a reasonably localized wave packet function, but also sufficiently broad that as time evolves, the kink has a relatively stable shape. And you can see that as time evolves, 10, 20, 30, 40, 50, the kink is indeed accelerating under the symmetry breaking potential. And if you look at what happens over larger time, so this is now a color plot of the same thing. So the initial state is down here. True vacuum on the left, false vacuum on the right. You see that indeed we accelerate, we reach some sort of a maximum speed, and then actually what happens is we decelerate, and eventually we go back in the other direction. Now, I'm referring to this kind of effect as a lattice effect, and I'll tell you why I'm going to think of it that way. So the dispersion relation of these kinks, as I illustrated on a previous diagram, looks something like this. It starts off at some initial energy. I've subtracted the initial energy, so it's 0 on this diagram. But there is a gap with the ground state. And you know, it's fairly quadratic at the beginning, and it sort of almost becomes linear, and then eventually it turns around and goes back to some almost constant value. And if you think about the behavior of the group velocity of a wave packet for this excitation, well then it's got its maximum velocity at around this location here. The velocity is just related to, proportional to the derivative of this dispersion relation. So it's over here. These blue circles show the actual velocity from the simulation, and the red curve is just the derivative of the dispersion relation with some prefactor. So indeed, we expect on the lattice there to be some maximum velocity, and after that, the velocity will decrease, and eventually it will turn negative. That is, if the momentum just increases linearly as a function of time. And indeed, the momentum does increase linearly as a function of time in our simulations. We can verify that. So you can equally well think of this, this axis as time, at least initially. Oh, there were some questions, so I'm going to answer those too. Is that a Bloch oscillation effect? Oh, okay, he answered the question himself. Okay, I see, it is exactly that. Yes, good. Actually, I didn't know to call it that, so yes, it's a Bloch oscillation effect. That's exactly what that is. I'm glad I know that term. I'm going to write that down. Hang on a second. Okay. All right. So because we're interested in the physics of an emergent field theory, we're interested in saying things about emergent field theories near the critical points of this model. We actually don't want to get into this regime where we go past this momentum and kinks start decelerating. We want to stay within the regime where we can imagine our lattice system is showing us some emergent continuum dynamics. So we're going to avoid that. Now let's get on to bubble collapse. So now I'm going to show you the evolution of an initial false vacuum bubble state with two kinks for two different scenarios. They're differentiated only by the value of this symmetry breaking field H. So one has a smaller value, one has a larger value. And what I'm showing you here are the dispersion relations numerically obtained for scalar particles in this model, topologically trivial particles. And I'm showing you twice the energy of these scalar particles and comparing that to the energy of the state that we construct. Why am I doing that? Because this is telling you about the likelihood of producing pairs of these particles. So if the initial energy has, if the state has at least as much energy as two scalar particles, then in principle we can produce two scalar particles in a collision, in a collapse. Now on the left case, actually the energy is not sufficient to do that. On the right case, it is sufficient to generate at least two species of scalar particle. So what does that look like? So here's the spin plot again. So that now we have a false vacuum bubble in red in the middle. And in the left case, we see that the walls of the bubble rush toward each other. They collide before we get this deceleration effect. So we are in our continuum physics regime, if you like. And they collide, and it looks as if more or less they bounce off each other. And as time goes on, things sort of get blurrier, they spread out, there's dispersion of the state. But let's contrast it to the case on the right. Here, we see that we, for the first collision, see something similar emerging, but then for future collisions, the bubble seems to get smaller, which suggests that it's losing energy. And if you look really closely, you can see a little line of something coming off to the right. And so I'm going to show another plot that zooms in on that regime. So now I've just changed the scale and taken values relative to the vacuum spin expectation value, so that you can see these small lines coming off to the right and left. So on the left, we have just a bubble. On the right, we have a bubble and some ballistic stuff rushing off toward the sides, coming out of the first collision. So indeed, it looks like we're producing scalar particles that are not confined by the symmetry breaking potential. We can also look at the entanglement entropy, and that shows a similar pattern. So on the left, no ballistic behavior. On the right, there's a faint ballistic shadow of these particles that are coming across to the left and right, which will generically be entangled with each other. And even after the second collision, it gets a bit more intense, so there are more particles being produced. Another thing to observe here is that the entanglement starts off within these kink wave packets as being quite small. It's really quite small, but after the first collision, it jumps up quite significantly. After the second collision, it jumps again. And the same is true on the right, only more so. We jump up again, we jump up again, the entanglement grows and grows. So the more collisions you have, the more the entanglement grows and the harder this becomes to simulate. And eventually we have to stop. Oh, I'm just going to mention, I forgot to say it. So here you can clearly see something is bouncing off the side of this plot. This is because it's meeting the edge of the non-uniform window that we set for this simulation. In principle, one can allow the window to grow so that bouncing doesn't happen. But for this simulation, we just shouldn't really trust things that happen much after the bounce. And there's a question, I'm going to answer that. What does particle, oh, okay, hold on a second. So question one, what does particle mean in this picture? Okay, which picture? Do you mean, oh, here, there's a clarifying question. Do you mean a localized wave packet or something else? So yes, I mean a localized wave packet. So this is an interacting system. So the only sense in which we can distinguish particles is if they are spatially distinct from each other. If they're too close to each other, they'll be interacting and it'll be hard to say whether we have, say, one particle, two particles, or three particles. But if they're spatially separated, we can count particles. At this point, all I'm really trying to show you is that there is something ballistic happening, which means that there's something that is not a pair of confined kinks coming out of these simulations. And I will get on to a better characterization of the content of that on the next slides. And Alex Boozer is asking, is the half-chain entropy just a partition along the center? So yes, the half-chain entropy is just is the entropy that I showed you on the MPS diagram earlier. It's just the entropy of cutting the system into a left and a right part. So the position of the cut is what this x-axis is here. So if you ask how much entanglement is there between the left and the right, then you just follow along the middle here. And if you ask, if you look at this cut here at, say, site 100, well, then it's showing you how much entanglement there is between stuff to the left of 100 and stuff to the right of 100. So the fact that it's slightly non-zero over here means there's something on the left which is entangled with something on the right. And here we think it's, you know, a scalar particle. Okay. So now let's get on to the particle content in a bit more detail. So I told you that we could use these quasi-particle position states and take overlaps with them to try and diagnose the particle content. That's a nice thing to do because you can tell whether it's working or not. If you have a full characterization of the content of your state, then the contributions will add up to 1. And if you don't, well, they won't. And there'll be some norm missing if you try to capture the state in these bases. So this is what we're doing here. So we have, I'm actually showing you 3 different bases, a 1-particle basis to capture stuff that's happening when everything's very close together. And you can sort of think of the mess as a single particle. There's a 2-kink basis, which is the one we use to construct the initial state, with 2 separated kink quasiparticles. And there's a 2-particle basis, by which I mean 2 particles separated by true vacuum in the middle. Now on the left, we didn't see anything ballistic, so we don't expect to see anything in this 2-particle sector. And indeed, as time evolves, although at the collision we see some jump in this 1-particle sector where stuff sort of smushes together, after this collision, things separate again, and we essentially have an exact characterization of the state in terms of the original 2-kink basis. So really, this is good confirmation that we're seeing elastic scattering here. The kinks are just remaining kinks. Nothing really is changing. They're just bouncing off each other. Now, as time goes on, things smear out. The collision here becomes broader, which means that this one particle basis has to do more work. But we still have overall a good characterization of the state, at least between collisions. The fact that we don't during the collisions is just an artifact of this one particle basis not quite capturing the full mess that happens when things smush together. And these wobbly bits at the end, by the way, are artifacts of the bond dimension becoming insufficient as time goes on and the entanglement entropy grows. Now, if we look on the right, it's rather different. The first collision, after the first collision, this 2 kink amplitude goes down by about 10%. And if we look at the 2 particle amplitude, well, it jumps up by about 10%. Not quite, doesn't quite sum up to 1, but it almost does. So we can see that we're characterizing the state pretty well using this 2 kink and 2 particle, using these 2 kink and 2 particle sectors, and that we have a roughly 10% chance of producing 2 scalar particles. Now, there are actually more details to this data that I could show you. For example, we can distinguish between the lowest branch of kink-like excitations that I showed you on the previous slide. We can distinguish between this branch and this branch to some extent. And one could extend this by looking at larger numbers of particles, but we haven't done that yet, essentially. We'd like to do more and better characterize this stuff. So now I'm almost done, but I want to show you a plot of how the entanglement entropy is changing as we change this H field. And now I'm talking about a single number. I'm talking about the entanglement entropy in this plateau region after the first collision, right in the middle of the chain. So for the middle of the chain, in this flat-looking region, a fixed amount of time after the first collision. And we can look at how that changes as a function of this H field, which effectively changes the energy of the false vacuum bubble because it changes the potential associated with the false vacuum. So I've used the energy as the x-axis, and I'm showing you the entropy as a function of this energy, and you see that it increases linearly, which means that at least while you're able to increase this H field without, while maintaining a metastable false vacuum, the simulation becomes exponentially harder. And this is because, of course, the bond dimension is going to have to increase as a power law with the energy in order to maintain the same accuracy for the simulation. This is because the bond dimension, again, limits the entropy in the way I showed you before. Now, again, the time cost of these simulation scales polynomially in chi, so we have an exponentially more difficult computation. Now, these entropies are all pretty small, which meant we could actually do these simulations pretty easily. But generically, this kind of growth is what you would expect when you make the simulation more energetic. That said, it's a little more complicated than that because if you look at how the entanglement changes instead of versus the field versus just the initial separation of the 2 kinks, so you can just pull them farther apart to increase the energy so that they accelerate for longer before they collide. If you just do that, then actually the entanglement entropy appears to plateau. And if you try to extrapolate it to the limit of large energy, then it does indeed look like it's going to some constant. So that seems to be a contradiction to what I just said. You increase the energy and it makes it exponentially harder. Well, that doesn't seem to be the case here. Well, what we're ignoring here is that the problem we're interested in is understanding the dynamics of the emergent field theory. And if we just increase the initial separation, we can't do that because there'll be a point where we encounter these lattice effects. The velocity gets to its maximum and then starts to decrease again. So actually, the thing we'd like to look at is how the entanglement entropy changes as we approach the continuum more and increase the energy in a way that avoids the lattice effects. To increase the energy avoiding lattice effects, we need to change Hamiltonian parameters and move closer to the critical points of the lattice model. So we're working on getting some entanglement characterization of that. There's a lot of choices you can make in taking continuum limits if you don't have a particular field theory you want to target. So yeah, we're working on simulations for that. Okay, so I've come to the end and I'm going to summarize. So I've shown you that we can construct stable dress domain walls or kink quasiparticles, and that they evolve roughly as expected if you include lattice effects in time. I've shown that you can that we can simulate both elastic and inelastic collapse of the false vacuum, and that we can verify to some extent the particle content and what's happening during these scattering events in terms of numbers of particles being produced and what are those particles in terms of the eigenstates of the Hamiltonian. So where do we go from here? Well, as I mentioned, we'd like to increase the energy while avoiding lattice effects. And that means looking at continuum limits and getting closer and closer to a continuum theory. This definitely makes the problem harder. For one thing, we have to use larger matrix product state bond dimensions to represent even the vacua. That's before we construct any excitations on top of it. And we have to make everything bigger because the size of the wave packet in terms of lattice sites just has to grow because your lattice spacing is effectively decreasing. It has to grow for one thing if you want your particles to remain reasonably stable with time and not to diffuse quickly. And we can, of course, look at harder models, not just modified Ising chains, in order to maybe explore physics that is closer to that of the phi-4 theory, or just more complicated physics involving more particles that are accessible. And of course, ultimately, it'd be nice to go to higher dimensional systems, higher spatial dimensions. One way of doing that with the current tool set would be to just have a small-ish compactified second dimension, such that we can still treat the system as quasi one-dimensional, as effectively one-dimensional. But that already will dramatically increase the complexity of the collisions of the scattering involved, because now we can indeed have an angular dependence on scattering. Okay, and that's it. Thank you very much for your attention.
Thank you for the great talk. We have we can take a few questions. We're like running out of time, but I think it would be nice if our so while people are thinking what to ask, you mentioned, can I ask you something? You mentioned that you can have different spreads of the wave packets.
Yes.
Did you like? I don't. Maybe I missed it, but like, how did you choose the right size? Like, I guess if
right.
it's too large, it's more stable, but simulation is harder, or you.
Well, so the simulation doesn't get massively harder if you increase the size of the wave packet. The cost of increasing the size is linear. You just increase the number of lattice sites, so that's not too bad. So we chose the size such that the empirical spread of the initial wave packets was not too bad, essentially. And let's see, it also affects the spread that occurs during collisions, so how quickly these bubbles blur out. We chose it so that we had, a system that could be simulated in a reasonable amount of time on, say, a few cores of the computational cluster at Bridge. And we did experiment with varying the size of the wave packets to see what effects that has, say, on the entanglement entropy produced in the collision. For example, for elastic scattering, in the limit of large wave packet sizes, the collision of two particles with the same momenta should actually produce zero entanglement because there's only one possible outcome in that case. in 1+1 dimensions. And we were able to verify that for the collisions of these confined kinks, that seems to be borne out up to a point. So there's a bit of a mystery there still. After a certain wave packet size, that relation changes and the entanglement seems to increase again. And I suspect this is to do with doing this with confined particles, but we haven't thoroughly investigated what's going on there yet.
Thanks.
Actually, I have a question real fast. So yeah, I guess, could you just maybe summarize, like, now that you've gone through it for the specific model, like what sort of what questions were kind of, I mean, I guess like, you know, the whole point of doing this is that it's kind of, the strongly interacting case is hard to access analytically. So like what, I guess like concretely, like, is it kind of like this is a behavior that we might have expected, but I guess we didn't know that it like would exactly happen at this sort of parameter settings. I don't know if you could talk more about like what did we learn specifically that we didn't know.
Well, so we indeed, you generically expect in some interacting theory that you would see inelastic scattering of these bubbles and some particles produced during collisions, but these simulations simply haven't been done before. So exactly what happens, what particles are produced, how many, and what happens to the bubble over long times, these just haven't been answered before, at least not at strong coupling. So the main purpose of this is to explore how this physics, explore how this physics occurs in spin chains and what phenomena can we access this way. And also to explore how well the computational methods that we have can handle this situation. If you ultimately do want to scale up to something that more closely mirrors the physics of, say, 5-4 theory or even the standard model, then this is a simple simple case on which to start. If you can't do this, then of course you can't do that. So, and part of the motivation is to understand if there is a wall that we will hit at some point, and there likely will be. It might be a wall, say, if you want to go really close to the continuum limit, at some point, your classical computer just has to be way too large. The cost grows exponentially and generically, so there ought to be a point where that happens. And there, you might want, say, to do this in a fully quantum setting using a quantum computer, using, for example, the Jordan-Lee Preskill scheme for simulating scattering.
So for like the 5^4 theory, like sending it to like closer to that, I guess the sort of, we're not sure that it actually, we will see this sort of behavior. And if we do see it, we don't know exactly like how it will evolve. And these are...
No, so nobody knows how exactly this collapse will happen in strongly interacting 5^4 theory. And so it will be interesting to find that out. And even 5^4 theory is, of course, a much simplified model, and there's a lot you can do beyond that. So, there's a question coming in on the Q&A. If we change the potential, there are a new set of energy eigenstates, and we can compute the transition amplitude of the original state to these new energy eigenstates as a function of time. But this is in energy space, so it is not clear to me why this process corresponding to a moving domain wall in space, why this process corresponds to moving of domain wall in space. There may be another situation in which you gradually change the potential locally, so it kind of makes sense. But it just seems that you are considering the first case where you change the H field globally. Okay. Yes. So we deliberately chose to choose the field, the H field, to be on globally, because then we can explicitly have the true vacuum state be, at least numerically, an eigenstate. So there's no evolution of that by itself. And the false vacuum state with a small value of H is also essentially an eigenstate. So by itself, it doesn't evolve. This is because we wanted to focus on the collision of the kinks themselves rather than looking at any processes that happen within the vacua. Now, it's certainly interesting to think about processes that happen within the vacua that might, say, seed a true vacuum bubble on the false vacuum. And we have some initial simulations relating to that, actually. For example, we simulated what happens if you collide two scalar excitations on top of the false vacuum. And indeed, they do generically seed a small amount of true vacuum. But those simulations are really at a very preliminary stage at the moment. We also did simulations just like the ones I'm showing you, but with not with a global field, but with a local H field just turned on within a window with the same parameters otherwise. And we can produce essentially the same phenomena. So we do have, in that case, quench effects, because the field you've quenched in a local region, that means that the vacua themselves do evolve non-trivially to some extent. But the evolution produces only very small changes to these simulations because of the smallness of this H field. So essentially, we reproduce the same phenomena in that setting. I hope that answers the question. I mean, well, there was another part of this, right? So why does turning on this potential just accelerate domain walls? Well, it kind of ought to accelerate domain walls, right? Because it's energetically favorable for to have more true vacuum and less false vacuum. So that effect ought to be in there. And of course, we observe that as well. And yeah, indeed, the rest of this, avoiding other effects like tunneling of the false vacuum to the true vacuum, we deliberately do that. We choose the field to be very small for that reason. Are there any more questions? Okay. 2 questions from Alex. What's the current bottleneck in your simulations? And have you thought about using shadow tomography to compute some of these observables? Okay, right. So the bottleneck in the simulations, I don't think we've reached it yet. We've done a lot of exploration. It took us a while to find cases where we were seeing genuine inelastic scattering. It turned out to be harder than we expected to locate inelastic scattering. We started with just the Ising model, and we were actually rather surprised that we never seemed to see it in that situation, even in cases where energetically it was allowed. So we had diagrams like this one on the right for the pure Ising model, but nevertheless, we did not see the production of scalar particles. So that seems to be, it was harder than we thought, than we expected to find these cases. The reason it didn't happen in the Ising model is related to some work that has been done on rare non-thermalizing states in exactly that model with the longitudinal field turned on to some extent. And it's probably related to the fact that the emergent field theory in that case is actually integrable, even if the spin chain is not. And it's been studied by people like Alexander Samologikov. It has some E8 symmetry, and it's reasonably well understood. We don't have an emergent integral theory, or at least not obviously in this case. So maybe that's why we're seeing inelastic scattering here. But going to much higher energies is going to probably deliver some bottlenecks. 2, have you thought about using shadow tomography? So, well, I guess you're talking about now doing this on a quantum computer, and I haven't directly thought about that, but I expect it's, is that what you mean? So certainly using, maybe you could elaborate on that question a little bit. Feel free to speak if you're able.
Can you hear me?
Yep, I can hear you.
Yeah, so I was just thinking about trying to simulate a real experiment. Like eventually you're probably thinking about simulating this on some quantum device.
Yes.
And there, one of the challenges, bottleneck might be computing these observables, like the entanglement entropy and that kind of thing. Mm-hmm. So I'm just curious to see how well those kinds of algorithms like shadow.
I see.
work in this setup with these kinks and particle scatterings?
Right. Yeah, I think that's definitely a very interesting question. I mean, certainly they're likely to be helpful. I think very helpful for some purposes. Like if we want to say measure the energy density, which is another way of seeing that there's you know, so this setting where we start off with confined particles essentially is nice, because if non-confined particles are produced, we immediately see this from seeing something ballistic flying away. And one way to see that is in the energy density. In fact, it's clearer than looking at these spin plots. So if you can use shadow tomography to compute the energy density easily, then that's great, or even the momentum density. Then that's another way of diagnosing particle content. Yeah, and I expect there's more to be done there, more to be said there too. But I haven't thought about it that much yet.
So I have a little comments about this tomography thing. I remember that their existing works have been done, I think have been done in the several occasions of spin chains. So for instance, there is a work by Fernando and et al. and Gan and Chen, and they did some quantum simulations for for some spin chains, and they try to simulate some near-term algorithms to find ground state. And I think they did some tomography thing for spin chains, but I don't really know if anyone has done any work in the context of high energy physics and particle scattering. Maybe it is an interesting direction to explore.
I see. Thank you.
Yeah. Okay.
So yeah, anything else?
It's probably a good moment to stop.
Yeah.
I think if there are like more questions, people can.
Yeah, sure, of course.
To you.
Sounds good to me.
Thanks again for the talk. I think it was really good. I think you did a very good job with answering questions. And
well, it's nice that I can immediately see that there is specifically a question with this Q&A thing. So that's definitely an improvement over just using the chat, say, or raising hands.
Yeah. Okay. Thank you.
Thanks.